Um, Hi everyone. I am Suprita, and I am a PhD scholar. And since I'm a PMRF fellow, I uh, will be taking your live sessions for the course Fluid Dynamics for Astrophysics, which you guys have signed up for. Um, so these sessions are going to be held once a week, as you guys might have been informed, and it'll be mostly from 7 to 9 p.m. on Fridays, unless there's an emergency from my end. Uh, the plan for these discussions is, let's say, for the first half an hour or 1 hour, I would like to give you guys a quick recap of that week's lecture, and I'll be discussing a few sample questions that will help you solve quizzes and assignment problems that you'll be assigned to be considered for grading for this course. And you can always interrupt me in between. And if you guys want, we can keep the Q&A sessions, which consists of doubts you might have from the lectures towards the beginning of this session or the end or the middle, whatever you guys prefer. I would like these sessions to be interactive, so because there's no point of me speaking for 2 hours. Um, so please feel free to unmute yourself or switch on video and we can have a discussion. Since this is just week one, I don't know how long this session is going to be, but we'll try to keep it interactive so that it doesn't get boring at any point. Uh, so if you guys don't have any immediate questions, I will proceed with recapping what was done in this week's lectures. Um, and just give me some time to change the layout because no, that's fine. Okay, so let's begin. So one of the first things that was discussed in this week's lecture is the concept of continuum limit, where we don't want to study the dynamics of each particle in the fluid system, but rather we would take up or we would look at the fluid as consisting of many fluid parcels. Now, the idea of the fluid parcels is that the way these fluid parcels are selected in your fluid system is that you will have a reasonable amount of fluid particles inside your fluid parcel, and your fluid parcel will be definitely macroscopic in volume. What it means is that it won't be too small, so that you still have a large number of particles inside this fluid parcel to be in the continuum limit, so that you don't have to bother with studying the dynamics of every single particle inside the fluid parcel. And you can just do away by studying the emergent phenomena of the parcel. And it also has to be, the fluid parcel also has to be small enough that you can consider many such parcels in your fluid system, and you can deal with the dynamics of or the properties of the fluid parcel to study the properties of the fluid as a whole. Uh, and one of the concepts that was also discussed is that macroscopic properties such as temperature or thermal conductivity, uh, these are emergent phenomena, and these have their what's responsible are microscopic properties of the fluid that results in these macroscopic properties such as temperature or thermal conductivity. Now, here is where I would like one of you to volunteer. Uh, can someone please tell me what you guys think would be responsible for, let's say, the temperature of a fluid, or what does it mean for the temperature of a fluid to be, let's say, T1? Anyone?
The average kinetic energy of the particles is Boltzmann constant times T1.
Fantastic. Really, really, really fantastic. Thank you. Thanks a lot. So, since we do not know what the velocity, or it's really impossible, really, to keep track of velocity of every single particle in a fluid system, because there are Avogadro number of such particles, so it's really impossible to keep track of which particle is colliding with what particle and then getting, or rather, what is the velocity of both of these particles changing to. It's impossible to keep track of that. Instead, what we will do is we'll study the average uh, uh, thermal energy of all of these particles in the system and call it temperature, right? So the microscopic property that gives rise to, let's say, the temperature is thermal motion, right? And similarly, let's say thermal conductivity. What would be responsible for thermal conductivity in fluid? Anyone? So things like
Trans-
transport, right? Thank you. Thanks a lot. Thank you. Things like transport phenomena, right? So once when an energetic fluid particle makes its way to the other end of, let's say, the container that contains the fluid, what you effectively see is that the temperature of this end rises, right? And this is the process of equilibration. This is the process by which the whole fluid would come to a certain temperature. That's and this happens by the transport phenomena of particles. And if we go the other way around, if we try to look at, let's say, the microscopic property of particle collisions, right? What macroscopic property can it give rise to?
Pressure.
Absolutely, right. Thank you. So it was also discussed in the lectures, but it was probably not explicitly derived. But it is very easy to see that these macroscopic properties can be derived in terms of these microscopic properties. So if you have a microscopic description of the property of the fluid, then you can derive or predict what, let's say, the pressure of a gas would be or the temperature of a fluid would be, right? So these things we can go from one description to the other, and these descriptions are related. And that's an important point that was made in the lectures.
Okay,
And
I have one question. May I ask it
yeah,
right now?
yeah,
The,
sure.
the question is that like Professor Prasad mentioned in his lectures that even the interstellar medium, which is extremely rare, it can also be treated as a continuum. But in that case, the number of particles will be very less. So in that case,
Right.
what will be the size of the fluid parcel in that case?
That's a good question. And these are the things that one has to keep in mind. So I do not have an answer because I don't know yet what system or what phenomena we're going to study. The size of the fluid parcel or on what scales you'll be studying the system, that really determines how good your continuum limit is. So one really has to keep in mind that when you're using this fluid description to study, let's say, interstellar medium, let's say to study electromagnetic fields in interstellar dust and so on and so forth, which you will be doing, not this hasn't been covered in the first week's content yet. One has to keep in mind that when you're using the fluid description, when you're using this continuum limit, how justified are these assumptions? And how well can you trust the predictions that are made by using these assumptions? Okay, so that's a very good question because one must always question whether the assumptions that one is making, how well do they hold, right? So, and how well can you predict uh, these phenomena? That's a good question, and that was what I was about to discuss next or recap next. Uh, So it's good to know how justified your assumptions are. And I think there was a point that was made in the video that if you are looking at water molecules at um, millimeter scales, then things can change. So you can't really consider fluid particles that are very, very small because right now you're completely classical and things might change. So you have to keep in mind that you have to deal with a fairly macroscopic volume and you have to deal with a fairly large number of particles in this macroscopic volume so as to not distort the continuum limit, as well as to stay in the limit where you have a fairly large number of fluid parcels in your in your uh, uh, I don't know fluid system in the container, such that this description can hold. So this is the premise on which you're going to build your next few weeks, right? This is the premise where you're working in the continuum limit, where you're not dealing with every single particle in the fluid parcel, and you're looking at the parcel and you're studying the emergent phenomena. Let's say you're focusing on the temperature or the pressure of this fluid parcels, right? Or the velocity of this fluid parcel. Instead of focusing on every single particle and the Brownian motion it suffers, you're not looking at at every single particle's motion. You're just studying the velocity of the parcel as a whole. Okay. Okay, so one other thing that you might have discussed or you might have heard about in the lecture is the velocity distribution. This quantity called the probability distribution function of the velocity and spatial position of the gas particles, right? So before that, I would like to ask you, what would be, let's say, a macroscopic versus a microscopic description of a box of gas particles? What would the microscopic description of a box of gas particles look like? Or what information do you have to supply uh, to uh, to give a microscopic description of a box of particles?
The number of moles.
But that would be a macroscopic description. I'm talking about description really. So if you just tell me the number of particles in the box, that doesn't quite cover it. Because all I'm getting to know is, okay, there are 10 to the power 23 particles in this box. But I don't really know the description of these particles. How energetic are these, right? Or how frequently are they colliding with each other? Right? Or if these particles have, I don't know, some other properties like electric charge, or if they're colored, I don't know what properties these particles hold. I just know the total number of particles in the box, and that is not a microscopic uh, quantity. But yeah, so any guesses? What would a microscopic description be?
The distribution, the velocity distribution, or the whether it is forming, it is following a Bose-Einstein or a Fermi-Dirac or this thing, Maxwell-Boltzmann distribution.
Okay, that's okay. I appreciate the enthusiasm. Okay, since we're still working in the let's say the classical limit where these particles are, we're not looking at the spin of these particles. But okay, yeah, sure. But uh, the
Can
velocity
I tell you?
distribution, yeah, sorry,
Uh, is it clear, right? So,
could
like
you please repeat?
macroscopically, we can deal with that pressure and tell you how much volume it have
Uh-huh.
based on
Mm-hmm.
things
Mm-hmm.
measure the pressure, right? Pressure, volume, and the temperature.
That's true.
So,
That's true. But let's say what would the microscopic description be? So microscopically speaking, it's as simple as the name suggests. I have to keep track of every single particle in the box. So I have to tell you what is the velocity of every single particle in the box of gas particles. But does the quantity PDF f of Vx cover this? This quantity, does this really tell you the velocity of every single particle? It doesn't. It doesn't, right? That's why at some point you must have noticed Professor Prasad mentioned that it's not quite a microscopic quantity. It's what people call a mesoscopic quantity, something in between microscopic and macroscopic. And these are the nitty-gritty details. One would usually not worry about these distinctions, but it's good to keep in mind that what this quantity tells you is not really the velocity of every single particle. It tells you that if you pick a random particle from this box of particles, then what is the probability that it will have a certain velocity? So if you look at the distribution of f with respect to v, it would have some peak like this, right? So where it peaks, let's say this velocity is v1. So v1 is the velocity that the particle randomly picked has is most probable to have. Okay, so it doesn't quite tell you that well, this is the velocity of the particle. It tells you that okay, this is the probability distribution, and the particle you have picked has this probability of having this velocity. Okay, so um, I hope that's clear. Okay, we are nearing the end of recap. So let's just very quickly, there was also this concept of distinction made between fluid and solid. So fluids can offer no resistance to shearing stresses. So when you apply a shearing stress, and I hope shearing stresses was clear from the videos that were uploaded, shearing stresses cannot be stopped by fluids and they flow in response to shear. And another property that arises in the case of fluids in response to shear is viscosity. So the layer that you're applying, so if you have a box of fluid particles and you have you start to look at the fluid as consisting of many layers, and let's say you apply a shearing stress to this particular layer, what happens is this layer will flow because fluids cannot offer any resistance. But as this layer flows, what will show up is a dragging force that will try to drag and slow down this layer, and this will happen in all subsequent layers of the fluid, and this is viscosity. And solids, as opposed to fluids, can resist shearing stresses, and the typical response in them is elastic, where there's a restoring force trying to restore the shape of the solid. Okay, I hope that's clear. So the next thing that was discussed is streamlines. So let's say you're looking at the motion of a fluid parcel, which is given by this line over here. And let's say the velocity vector of the fluid is u vector, right? And the magnitude of the velocity is, let's say, q, given by the direction u cap. Now, at every single point, if you can find the local direction of this velocity, that is something you would refer to as the streamline. And the way it was defined was uh, ds would be dx dy dz. What this means is it is dx I cap plus dy j cap plus dz k cap. I, j, k is being the unit vectors along the three Cartesian coordinates. And the way the streamline is defined is via this relation. Now, can somebody tell me why is that?
Actually, I have tried to prove it. Actually, I found that all these things is equal to dt. So is it a correct way of thinking?
Absolutely. Very good, very good. That's fantastic. That's absolutely right. So what you're really looking at is a fluid parcel moving with velocity ux, uy, uz in along xyz directions. And if you have to find the infinitesimal displacement of the fluid parcel in the time dt, as the fluid moves with velocity ux, uy, uz along these three directions, then you're looking at infinitesimal displacements dx, dy, dz along these three directions. But now you have to find out in what time they have to be covered in the same time, and that is exactly given by this relation. Thank you, Aniket. Thanks a lot. That's absolutely right. So another definition for the streamline that was given is that ds cross u is 0. And once again, very simple. Can somebody tell me why is that? Anybody? Anybody? I mean, don't be afraid of. I mean, do not be. There's nothing to be embarrassed or scared about. If you're wrong, then I'll be glad that you're wrong, so that I get to explain why you're wrong. Please volunteer. Please volunteer.
Actually, it follows from the previous one.
Right, right, absolutely, absolutely. If you know that ds is the infinitesimal displacement of the fluid parcel along the direction, along the velocity, then you would know that you're talking about infinitesimal displacements along the velocity vector. So they're parallel. So of course the cross product would be 0. Is there somebody who is confused about this? Is it fine by everybody?
Yes, it's clear. It's clear.
Yes, do you want to say something?
Yes, it's clear. I
Okay,
think
okay, thanks a
clear.
lot. Thanks a lot. Okay. Uh, I know that these topics might be very simple, and since it's just week one, but I will be anyways be stopping for anybody who might be facing trouble in this. Please do not hesitate at all. These sessions are 2 hours long, and they are 2 hours long so that you have ample amount of time to unmute yourself and speak to me. Okay, so do not be hesitant at all. Okay, so if that's fine, I'll move on to stream functions. So the way stream functions was defined is, and this is important, if you have a fluid flowing in a plane, in the xy plane, let's say, then the stream function psi xy is defined as, is related to the velocity vector u via this relation. And know that the fluid is flowing in the xy plane. And when you take curl of something, and of course psi is a scalar quantity, it does not have a direction. So what you do is you take psi and you take it along z cap. You just write a z cap over here. And when you take a curl, you know that the curl is going to be perpendicular to the z-axis, which gives you a vector in the xy plane. And that's fine because we were considering velocity fields in the xy plane. We were considering flows in the xy plane. So that's exactly why we needed to uh, write psi with a z cap.
Excuse me.
Yeah, yeah.
Actually, as per the lectures, as per Professor Prasad, whatever he said that these things are valid. Means this we are considering this as a 2D flow. But what will happen if it is a 3D flow? Means there the z cap direction is also used up. So in that case, then with what
You
unit vector should
probably
we?
don't. So we'll cross the bridge when it comes to it. But I think the utility of stream functions as of now it has not been discussed yet. Like the applications has not been discussed yet. So as of now, stream functions are something that we consider to be conserved along streamlines. And in fact, we can define streamlines. I wouldn't go on to say define, but we can look at each streamline as being characterized by a stream function. So streamlines are whatever that's a particular stream function is conserved along. Right? So let's just look at, I understand your question, but we'll cross the bridge when it comes to it. We'll probably not need to consider stream functions along three directions because that I think defeats the purpose, but that's a good question. Okay, I might also think about it. Okay. Uh,
Okay,
what?
and
Hmm.
what is the stream function physically? Because there is no, it is just a mathematical definition, and there has been
Yeah,
no.
so physically you the way to look at it would be it's a quantity that is conserved along a streamline. As simple as that.
Okay.
As of now, no other physical applications. If there arise in the future, we'll get to it. But as of now, you're just supposed to look at it as something that is conserved along a streamline.
Okay.
Okay, cool. So there was an exercise in the lectures to show that the stream function is. Was it a question?
What is the dimension for this streamline function? So dimension.
I'm sorry, Prakash, you're not quite clear. Can you repeat your question?
What is the dimension formula for the stream function? Right? You have
Dimension as
any
in
idea about
dimension
it?
as in mass dimension?
Dimension formula for the stream function.
Unit?
U. So
Units?
is equal to plus. Is it clear, right?
I really don't understand. What do you mean dimension of the stream function? I'm sorry, Prakash, could you type your question? I think that will be better since your audio seems to be distorted or there's some problem on my end. Do you mind typing the question? Okay, so we'll continue and I hope you're typing the question and I'll answer it when I see it in the chat box. So there was an exercise in the lectures to show that the stream function is conserved along the streamline, which is to show that del psi, which is del x psi dx plus del y psi dy is equals to 0. And has anybody tried this out, by the way, before I move on to?
Yes, I have tried it.
Okay, that's great. So, what do you start with? Could you?
First, I just started with the definition of stream function. Then, it is the curl of this one. Sorry, the u is equal to minus of curl of this one
Mm-hmm,
of the stream function,
mm-hmm.
and then I applied this ds cross u is equal to 0.
Great, great, absolutely. That's very good. That's very good. Thank you, thank you.
Hmm.
Um, mean free path.
Okay, okay. So, do you want me to
No,
continue?
no, no, no. I'll take it from here. Thanks a lot. Thanks a lot. That's fantastic. I'm glad you've tried it. I hope other people are trying it as well. I mean, it's interesting to think about it. I hope all of you are trying it as well. I apologize. Nothing to apologize about. Yeah, please go ahead and type your question in the chat box. I think that's fine. I mean, it's unfortunate that this is online. So, mean free path. Do you want to see something, Siddharthan?
No, actually, microscopic description you said, right?
Okay, I'm so sorry. I'm probably not noticing the chat box as I'm speaking. Please feel free to unmute yourself and talk
Yeah,
to
okay,
me.
okay.
Cool, cool. Thanks a lot. Thanks a lot. Yeah. Uh, okay. So as um, is there a text? Yeah. As Aniket mentioned, so what we're going to do is let's actually compute this cross product, and you will see that you have components along x and y as expected. Now, since we discussed this previously, that ds cross u is supposed to be a null vector, you actually go ahead and compute this cross product as well. And once you do it, you will see that you have some x component, some y component, and some z component. Now, since this is a null vector, all of these components are individually supposed to go to 0. And you will see that if you consider the z component, you will see that this is actually 0. This is the general idea. The calculation details are missing. And it's pretty simple. I hope you guys, after this, I hope you guys try it out yourself and see it for yourself. Okay, so what this tells you is stream function. Supposed to look at it as stream function is a physical quantity that's conserved along the streamline. So for every streamline, you have each stream function that tells you that that characterizes the streamline. Okay. Next, there is something called an irrotational flow that basically told you that if the curl of u is 0, that tells you that the fluid is the flow is irrotational, right? Because the curl of the velocity vector is 0. That's what irrotational in its sense means. Now, if you have such a velocity flow, then you know that you can write this velocity vector as gradient of a scalar quantity. Why? Because curl of a gradient is 0. So for irrotational flows, you can write this, and then you can show that this holds true. Now, has anybody tried this once again? And if you have, then would you like to share the general procedure that you took? Any volunteers? Okay, that's fine. That's fine. I would really encourage you guys to think about this because it's quite interesting and it's quite simple. Quite simple. It does not really take a lot of time. So I would really encourage you guys to perform these exercises because while performing these exercises, you really get a lot of insight into what is going on. You have to think about what it physically means. So it might also help you guys gain some physical insight as well. Okay, so what this means is uh, since u was curl of psi minus curl of psi, and for irrotational flows, it is also minus grad of phi. You can relate grad of phi with curl of psi. And if you do that and compute the x component and y component of grad of phi, you will see that just from this equation and this equation, you can compare the I cap and j cap components, and you will see that the x component of grad of phi is this, and the y component of grad of phi is this. Uh, Next, what you will do is you'll compute grad of psi, and you will see that it's just this. This is the formula for gradient. Now, if you take dot product of these two things, you will see that it's 0. Why? Because I cap components multiply to give you del x psi del y psi, and j cap components multiply to give you once again del xy del y psi, but now with a minus sign, and that gives you this thing. Cool? Is that fine? Yes, no, maybe? Anybody? I would really like a participation, just a yes or a no as participation from you
Yeah,
guys.
it's fine.
Okay, thanks a lot. Thanks a lot. Now, there was a passing comment. Thank you. So there was a passing comment that Prasad mentioned in his lectures that this relates to the Cauchy-Riemann conditions. Now, if you guys remember, Cauchy-Riemann conditions just tells you whether a function is a complex function is differentiable or not, and the condition was that if f which is a function of x and y. It's a complex valued function. If you write this as some u x y plus I v x y, where u and v are real functions, then Cauchy-Riemann conditions had equations consisting of partial derivatives of u v with respect to x and y, and they looked exactly like this. So that's why Prasad was trying to draw a parallel, and he said that many of these problems in complex analysis can be translated or looked upon as stream functions and these uh, scalar potentials, the scalar potential phi, stream function psi, and then you can do a lot of things. Now, what is something we'll look at later on, but this is just a passing comment. So, okay. Finally, onto the sample assignments that will help you guys solve the quiz problems that have probably been uploaded already on NPTEL site.
Okay, so actually, as you said about this complex analysis thing, so
Mhm.
actually, is the knowledge of complex analysis a requirement for this course?
Absolutely not. Absolutely not. Absolutely not. This is just to not make you question your life decisions of doing this, because at some point you might feel, why are we doing stream functions, right? So this is just
Okay,
to say that, well, this has practical applications as well,
okay,
right? So and since this is all just defining new functions that will, of course, help you later on and will be used later on in the lectures, but right now you don't see the application, so this might be you might question, why is it relevant? So this was just an example of where it could be applied. Is that fine?
okay.
Okay, cool. Uh, so before I proceed to, can this need to be recorded and shared? It will actually. Thank you for reminding. Let me just check whether it's still recording. Yeah, I hope it is. So all of these meets will be uploaded on YouTube, and the links will be shared with you guys. So these meets are recorded and they'll be on YouTube. Okay. Are there any? Let me just check the chat box really quickly. Okay. Okay. So the first sample assignment problem that will help you guys to do the quizzes. Uh, let's get on with it. If there are no other questions regarding the recap, and we can come back to questions later on if you have it. Okay. So the first question tells you, let's say you have two identical containers. One container is filled with water, the other one with oil, and you have a breeze blowing over the top of the containers, right? So, of course, you have to look at the breeze as a shearing stress. Now, you have to choose which of these following four options are true. So, let's move on to the first option. The first option tells you that the horizontal component of velocity of the oil at the very bottom of the container will be zero.
It is true
That's great. That's great. And why do we expect that?
because the fluid parcel sticks to the bottom of the container.
Right, right. Because the way we have uh, modeled, or the way one of the assumptions of our of setting up the premise was that what viscosity will do is it will make the fluid layer, which is right next to the right on top of the solid, will stick to it. There'll be no velocity for that particular fluid layer, and by the time the shearing stress, the effects of the shearing stress travels layer upon layer right down to the layer that is sticking to this bottom of the container. The effects will die down, and the velocity of this layer will be zero, right? So it is probably true that option A will be correct. Okay. The next option is that the vertical gradients of the horizontal component of the flow velocity will be the same for water and oil.
False.
Great, thank you. And what's the reason? What's the reason?
Since the viscosity and
Absolutely, as simple as that.
is
As simple
different.
as Absolutely, as simple as that. Great, thanks. So just to repeat, Since the viscosity, we expect viscosity of water and oil to be different, and the vertical gradient of the horizontal component of the flow velocity, which is nothing but the viscosity for water and oil, will be different. That's why B is not true. Now, is this point not clear to anybody? Why the vertical gradient of horizontal? That's a lot of words. If I tell you, it will just take half a minute. But is this confusing to anybody, or do you guys all agree that this is viscosity?
Actually, I have one thing to ask regarding viscosity. Can I
Mhm.
ask it right now?
Sure, sure.
Okay, actually, the thing is that means as Professor Prasad wrote down that Newton's equation of for this viscosity, he is defined that to be he called that the coefficient of dynamic viscosity. So, is there
Mhm.
anything called coefficient of static viscosity as well?
Viscosity as a property is dynamic, right? I don't
In the
think so.
in the video, he said coefficient of dynamic
I know, I know,
viscosity.
I
So I
know,
got
I know, I
confused a
know.
bit.
Equivalent to static viscosity. I don't think so. No. Viscosity as a property, you would expect it to be dynamic. And of course, uh, how would I get back to you on this? There might be something, I don't know, there might be something. Uh, see, I just don't want to say no because there are stranger things in this world than I can imagine. But of course, you can understand that viscosity is a property of transport of matter. It arises because you have one fluid layer uh, moving on top of the other, and the other one is trying to drag it down. It's a property that arises because fluid layers are in motion, right? So, of course, I'll get back to you on this, but I don't think so. No. Okay.
Okay.
Okay. Uh, okay. So the third of so B is probably not true. Not probably. Well, so B is not true. Now, as for option C, the horizontal component of the velocity of oil at the very bottom of the oil container will be the same as the horizontal component of velocity of water at the very bottom of the water tank. Is this true or false?
It's true since this is zero for both of them.
Great, great. That's great. So since it's zero, as Rohit said, since it's zero for both, so this is true. D. The horizontal velocity component of water at the surface will be the same as the horizontal velocity component of oil at the surface. Is this true or false?
This is false, I think.
Great. That's great. Why do you think so? Tell me.
Ma'am, because of the difference in the viscosity of both of them. The viscosity of water is very less as compared to the viscosity of, I think it's
Uh,
oil.
I think your answer is right, but so what I think is since the shearing stress, which is I'm assuming the breeze is blowing and applying shearing stress right at the surface. Oh, you're saying okay, okay, yeah, that's a great answer. Yeah, you're right, you're right, you're actually right because the horizontal velocity component will depend on what is the viscosity with which or the dragging force with which the layer right next to it is dragging it down. That's absolutely great. That's absolutely true. That's right.
Ma'am, can I answer this? Aniket Ganguly's the last question.
Uh, which one? Is it on chat or?
Why is it called the dynamic,
Yeah, please go ahead. Yeah, sure, please.
viscosity?
Yeah, yeah,
Ma'am,
sure.
I think the viscosity is a type of frictional force. It's a kind of friction, but in the liquid.
Absolutely.
Till now
Absolutely.
we
Yeah.
known about the solids, but now it's just in a liquid.
Hmm.
Now the friction has always its role when there is relative velocity. Friction has no
Absolutely.
role until and unless there is no relative velocity.
Absolutely.
Friction always it opposes the relative velocity between two
Okay, so you're
layers.
saying that it has something, you're drawing a parallel between dynamic and static friction.
Yeah, that's the dynamic. Until and unless you don't have a relative velocity between two layers in the
Yeah,
fluid, so you will
yeah,
not experience any this viscosity or viscous force,
absolutely.
because you are applying a shear force on the top, and there
Hmm.
is a establishment of this velocity gradient. So that's when
Yeah,
there is a relative velocity across each every layer. So you are
yeah,
getting a viscous force.
yeah.
That might be because that is called might be like this dynamic viscosity, not a static one. That
Right,
might be
right.
the reason.
Yeah, I
So
think I
Okay. Thank you.
agree. I think I agree. That's nice. Thank you. Thank you
thank,
for that comment. Yeah,
thank you.
great. Okay, that's great. So the answers are A and C. Okay. So the second problem is let's say we're considering a horizontal pipe. The two ends are labeled A and B, and water is flowing from end A to end B. Uh, and you're supposed to assume incompressible flows. So the pressure is not that high that you're supposed to assume the density of the fluid is somehow changing at every point in this pipe. You're supposed to assume that this fluid is incompressible. The density does not change, and it's simply flowing from end A to end B. Uh, and the pipe, as you go from A to B, the cross section area increases. Uh, Now, option A tells you whether the pressure at end A is less than the pressure at end B. So, is this true or false?
It's false
Great, great. Why is that?
because water always flows from higher pressure to lower pressure.
Absolutely. So, fluid flows, the property of flowing would arise because you have a pressure difference, and otherwise, you don't have a flow. So, it's absolutely not true that pressure at end A is less than pressure at end B. So, the second option is that the velocity at end A is greater than the velocity at end B. Is this true or false?
False, because if according to Bernoulli's theorem, this if pressure is high, then velocity must drop.
Uh, that's not quite true.
Ma'am,
Yeah,
that might be because of the continuity equation.
yeah,
Uh,
yeah, yeah, yeah.
A1 V1
Absolutely,
equals to A2 V2.
absolutely,
And
absolutely, absolutely.
inversely proportional area and velocity. That might
Yeah,
be the
yeah.
reason.
Okay, okay. So, Aniket, I think the idea is that since um, it's incompressible, and we know that we have not. You will come to it when we cover conservation of mass and momentum and so on. We'll come to things like continuity equations, and which will tell you that if you do not have water leaking anywhere in this pipe, right? So whatever amount of water is going in from end A is coming out at end B. And since the fluid is incompressible, so the density of the fluid remains the same, you have something called, correct me if I'm wrong, rho AV at end A is supposed to be rho AV at end B, where the area at end A is A, the area is A and velocity is B. So if the pipe tapers from B to A. So if it's thinner at end A, the velocity is supposed to be higher at end A.
Okay.
Okay? Does that make sense? Even intuitively, even without going into, because I shouldn't even have to resort to those equations because we have not covered it technically. So just even without doing any of that, you can feel greater velocity of the pipe. Just intuitively speaking, if the flow is incompressible, and if you will decrease the cross section by pressing down upon some section of the pipe, you can expect greater velocity because more water is trying to rush through it. You can expect greater velocities
Okay.
because the same amount of water is going through each cross section. Does that make sense?
Yes. So the answer is continuity equation and not Bernoulli. So that's the mistake.
Yeah, 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 yeah. Let's not even resort to equations yet because we're not technically supposed to resort to equations yet because we have not covered it, but just intuitively speaking, okay? So the third option tells you that the amount of water near end A is less than the amount of water near end B, and as we've already discussed, that's not true because there's no sink or source throughout this pipe. There's no mention of water leaking or water being added anywhere throughout this pipe. So the amount of water that's going into end A is coming out of end B. So option C is not correct. And D, the density of water will vary with the cross section of the pipe. Is this true or false?
False, because it is incompressible flow.
Absolutely, absolutely. That's right. That's right. So the correct option is option B. Is this clear? Shall we move on to the next question?
Yeah, ma'am.
Okay, thanks a lot. Uh, okay, so the third question is where we have to compute velocity distribution. Sorry, suppose we're given the velocity distribution of a Maxwellian gas. So this F is maximum Boltzmann distribution, and we want to compute the pressure of the gas. So to compute the pressure of the gas, what are the things we need to compute of this F? Now, I hope you remember what the first moment, the second moment, and the zeroth moment of the velocity distribution was. If you don't remember, the first moment was VFV, TV. second moment was v square Fv dv, and so on. First, you just multiply the velocity v, you multiply to the probability distribution and you integrate over the velocities, and that gives you the first moment, and so on and so forth. So the zeroth moment would just be Fa dv. Okay, now to compute the pressure of the gas, the pressure of a system of gas particles is given by what? It depends on what quantities?
Half mn v square.
Uh, no. Half mv square is not quite the, that's the thermal energy, let's say, right? So if v square is the average of square velocities, half m square mv square would give you, let's say, the average thermal energy of, and that is something we will require in this computation. But let's
Okay,
say,
it's p into v. Sorry. It's p into v is equal to half mn u square. I got
okay,
confused.
right. So the pressure is actually given by the number of gas particles times the Boltzmann constant times the temperature of the gas. And if you look at it, N and T, this is just a constant, N and T both are macroscopic quantities. And since they're macroscopic quantities, this is something we can derive from the mesoscopic quantity F. Now, all we have to find out is what N and T are, whether they are the zeroth moment or the first moment, what moment of the velocity distribution are N and T. So let's first focus on N. What is N? What exactly is N? How do we get N from F? N is the uh, number density of particles, which is to say that per, let's say, in unit volume of the gas, what is the total number of particles? And this would consist of all sorts of velocities, right? So how would I compute this quantity? Any volunteers?
By simply integrating.
Absolutely. So if you remember, this F gave you the probability distribution of velocities. So if you forget about the probability distribution and you just want the total number of particles, what do? You integrate F over all sorts of velocities. That gives you the total number of particles. Is this not clear to anybody? Do you guys agree with this?
So it's basically the area under the curve, Maxwell-Boltzmann curve. That's what you're talking about.
Yeah.
It's okay. It's okay, right?
Okay, cool. If it's not clear to anybody, we can come back to this later. But so N is going to be the zeroth moment of the velocity distribution function, right? And what is T going to be? Which brings us back to Aniket's answer, because this is something we required. What is T going to be? Okay, so T is this thing, right? It's half mv square. But what is this v square? Which particle do we pick out, and which velocities do we look at and square it to give us this T? This v square is actually the square average, the average of the square of the velocity of the particle. And to compute any sort of averages, we have to take the weighted average, right? Because not all velocities are equally probable. Some velocities are more probable than the others, and that is given by this quantity f. So we have to weight each probability by, and see that which probability is uh, more probable than the other. That is what gives us this average energy half mv square. That's what gives us the temperature of the gas particles. Now, how do we take this weighted average, and what gives us this weight? This weight is given by this probability distribution function f. And to do that, we have to integrate it with respect to f. Is this clear?
Yes, it's clear.
Okay, thanks a lot. So what we have to do is we have to integrate v square with fv, and that is basically the second moment. So we are done. We know that to find the number density of particles, we have to compute the zeroth moment, and to compute the temperature, we have to compute the the second moment. Is this clear? Is this clear why we are calling this quantity as a zeroth moment and this quantity as a second moment? That's just because of the power over V. Okay? So the answer we reach is B and C.
Ma'am,
Yeah.
could you go to the previous slide? Ma'am, why it's like temperature equals to half mv squared you have written?
That is because that's how we associate the idea of a temperature to a system, right? What is the temperature of a system? And why do we
Ma'am,
need
it
to
should be
bring
okay, ma'am. It should be like the average kinetic energy should be equals to half mv, that the bracket one, this RMS velocity. But why it's temperature equals to half mv square? Even its dimensions are not matching.
uh the mass
Like
dimensions
temperature,
too much, right? The mass dimensions too much, right?
ma'am. Like
This is
I'm
energy
telling
and
like
this is energy.
ma'am, I'm telling this temperature T equals to
Uh-huh.
half mv square.
Uh-huh.
So like so it should be like how temperature is the like dimension of T, and you are having this m and v square. The dimensions are not matching. So how could you write T equals to half mv RMS square, like the average
The
square?
mass dimensions are matching, right? If the mass dimensions of V is zero, its velocity.
Nah, yeah, it's okay. Go on. I'm just listening.
Yeah, okay. And the mass dimension of M is 1, and the mass dimension of
Uh,
temperature is also 1.
oh, okay.
Okay. You would
Yeah.
expect, so what other, how do you want to write T as? What do you want to write T as? And of course, I'm not asking you to actually compute V square. And all I'm saying is to get an idea of T, you need to compute the second moment of the velocity distribution function, because the second moment will give you an idea of the average square velocity, and that is related to the average kinetic energy of the. I should probably write this as TE. This is where you guys are confused about. Okay? And that is related to the temperature of the system. That gives you the temperature of the system. The average kinetic energy is related to the temperature of the system. Of course, then you have this equipartition theory where you are relating this. There are some degrees of freedom, and there's some way of relating this kinetic energy to the temperature of the system. Of course, yeah, you're probably right.
It's okay.
Thanks for pointing it out. Thanks for pointing it out. Yeah, yeah.
True.
The measure of the temperature of the system is given by the second moment of the distribution function. Yeah.
It's okay.
Okay. Any other questions? Okay. If not, let's move on to the fourth question. This is the second last question, so we'll be done soon. I guess you guys are tired. So please just bear with me for some more time. Okay. The next question tells you that you have two gas containers. One is cylindrical with some radius and some height, and the total number of molecules in this container is 2500. And the other one is a sphere with some radius and 3500 molecules of the same gas. Now what you're doing is inside this cylinder and inside the sphere, you are considering a very small volume uh, of length 1 centimeter inside each container. And you are asking whether this is a good approximation, or this is a good limit to work with the fluid description. So to determine whether fluid approximation will hold true or is justified, what do we need to do?
That the number of particles inside a finite volume is much more than one. That's
That's
the
true. That's absolutely true. That's absolutely true. That's a very good answer. It's just that it's just missing one small part, which is that along with considering the number of particles in each fluid parcel, you'll also have to consider the dimension of the fluid parcel that you're considering, or rather the length scales at which you're considering the fluid parcel. So the condition is not just that n is much, much greater than 1, but rather that, so because this n is going to be the total number of the total number density of particles in the whole this A and B, right? But how do I know whether this fluid parcel that I'm considering of 1 centimeter, that the small volume that I'm considering of 1 centimeter, uh, is a good approximation to work with, is a good volume to work with if I want to apply the fluid approximation to it? What I'll do is I'll take this small n, which is the number density of the fluid particles in A and B, and I will compute the volume of this small container, which is 1 centimeter cube, and I'll check whether this is much, much greater than 1. Okay, is that fine? Yes, no, maybe. Is that clear?
yes.
Thanks,
Ma'am,
thanks.
ma'am,
Yeah.
what should be the limit actually? You're saying much was greater than 1. So approximate the 10 to the power 23 we could take, like, what's the, it's a fuzzy boundary, it looks.
It's a fuzzy boundary. That is well accepted. That is there is no we're not pretending that we know what the limit is. That is a fuzzy boundary, and it's good to accept that. Okay, it's a fuzzy boundary, and I think we'll uh, see, because there's a simplifying assumption that we would like to apply to very complex systems that we have no way of studying each particle about.
Hmm.
So this is a simplifying assumption that we would like to use to simplify our lives and have a hope of at least studying the system to some zeroth degree, have some basic understanding of or make some basic predictions about the system of a complex system, as complex as, let's say, some intergalactic medium, some astrophysical system. And it's those are very high ambitions. So we must know how good our approximations are. So the better this gets, the larger the better this limit gets, the larger number of particles we have. And of course, it can't be too large, because then you run into many problems of, then you have to consider more complicated things like the spin, whether you're running into some trouble about accommodating this. Those are much more complicated things that we hopefully won't encounter here in this course. But uh, we have to at least keep this in mind, that to work with the fluid approximation, we should have uh, we should have at least a reasonable number of fluid particles in this parcel.
Okay, as you said, we must not have too many particles. Then in a gas we have Avogadro number of particles, so that is also too many
Forget
particles.
about that comment. Forget about that comment. Avogadro number is not going to be a problem. Forget about that comment. I should probably not have made that comment, because we are not there yet. But know for now that we are working very classically, and we are supposed to consider macroscopic volumes, which has a reasonably large number of fluid particles in this fluid parcel. And yet this fluid parcel is small enough so that we can consider many such fluid parcels in the entire container. So there are this is the premise of a fluid description. Does that make sense? Is that fine?
Yes.
Okay, thanks a lot. So, so the number density of the the particles inside container A is, if you take the total number of particles divided by the volume, it will turn out to be 3.18. And if you do the same thing with B, it will turn out to be 1.63. Now these are greater than 1, but these are not much, much greater than 1. So which one do you think is the correct option out of these?
D.
Great, thanks a lot. Thanks a lot. We would not like to call 3 or 1.63 as a number much, much greater than 1. We would have been happy if this was, let's say, 100. Not too happy, But if this were, let's say, 10 cube or 10 4, we'd be much happier because that is a number much, much greater than 1. We're not happy with 3.18 or 1.63, and we'll go with option D. And that is the correct answer. Is it fine? Can I move on to the next question, the last question for today?
Yes.
Yes, ma'am.
Okay, thanks a lot. Okay, so the last question is probably something that is there in your, I'm not sure, but it is probably a part of your quiz one. But I saw a question posted on the forum, and I thought that it is probably good for me to discuss this question once so that you can make your choice wisely. So if you're given, let's say, the velocity, the x component and y component of a two-dimensional flow, and you are asked to make a comment about this flow, whether it is a rotational flow, whether it's an irrotational flow, whether it converges at some point, whether it diverges at some point, whether it's diverging from some point. What do these statements mean? What does it mean to say that a flow is divergent or convergent at a point, or whether it's rotational or irrotational? The best way to handle these questions is to actually plot the flow. Now, what does it mean to plot the flow? Here is how you plot the flow. So let's say you start with, I should probably use, let's say you start with x and y planes, right? The next thing you do is you pick different values on this plane. Let's say you pick xy11, xy22, x1y0, and so on. And then you find the values of ux and vuy corresponding to these points. And then you plot the vectors with x component as this number and y component as this number. So you'll have a vector assigned to each point. For example, if you plot xy11 with this flow, what will you have? What will, let's say, xy, you're plotting the velocity flow for the point 11. What is ux going to be? All you have to do is substitute this value in the expressions for ux and uy. So what is ux going to be for 11?
Minus 1/2.
minus
Great,
half.
great, great, thanks. And what is uy going to be?
The same.
Great, thanks. Let's see for 2, 2. What is ux going to be? Right? So what you have to do next is plot a vector at xy equals 1, 1, the vector being ux I cap plus uy j cap. Whatever ux and ui values you find for whatever points you have chosen, you have to plot this vector ux I cap plus uy j cap at each such point. That is how you plot this velocity, this flow, this two-dimensional flow. Is it clear?
Yes, ma'am.
Okay, cool. Thanks. So instead of doing this manually, I have chosen to plot it on Mathematica. Uh, please do the hard work once and then you can switch over to Mathematica. Everything can be done with Mathematica these days, but anyway. So if you plot this, you will get such a uh, uh, profile for the fluid flow. And you can see that, let's say for x, so this is the x-axis, these numbers are x-axis, and these numbers are for the y-axis. And you will see that for a point 1, 1, which is such a point, the vector, the velocity vector is directed along minus half, minus half. So this is the profile for the fluid flow. Okay, now that you know this, what you can actually do is go ahead and compute the curl of this vector field. And if you do it, you'll see that it is 0. And there is also something you can make out from this profile because there is no curl to this profile.
Yeah, true.
Nice, thanks.
Actually, I tried computing the this divergence and curl of this one, but it was getting too complicated.
Oh, no, it won't get too complicated. So okay, let's try to why should it get complicated? So the curl would just be, I cap, j cap, k cap. I hope you guys don't get too bored. I'll be very quick. I know you guys know this, but please don't get bored. So you know that the user component is 0. This is nothing. And UX and UI are not dependent on Z. So all you'll be left with is this I cap del x UI minus del y ux minus j cap and so on. It might get tedious, but if you just follow through, I think it shouldn't be too big of a problem.
Okay.
Okay. It might get tedious because you do have you. I understand that, but I mean, it's unfortunate.
Uh, I initially thought that because it was getting so complicated, I thought that I must be wrong. So I abandoned that one.
Okay. Yeah, I understand that. But yeah, no, I think it's just good to do this once, this computation once, and then you must be, and then you'll be done. So, okay. So, what does it mean for a flow to radially converge or radially diverge? I hope so. Just for once, I hope you guys made the correct choice now. That radial convergence or radial divergence. I'll get to the question in the chat box in a minute. Radial convergence or radial divergence just means that all the velocity vectors, all the vectors are pointing radially in at a certain point. So they're converging at a point, at any point, doesn't have to be the origin. At some point, they're radially converging. And radially diverging just means the opposite, that they're radially outwards. That's it. And option C and D would suggest that the fluid velocity vectors are flowing in some direction would that has some rotation associated to it. That the vectors are in some net sense rotating. So if you add up the vectors, you will see that the fluid parcels are actually rotating about some point. So I hope now that you have this velocity profile, you know what this velocity profile looks like, you'll be able to make the correct choice. The velocity vector diagram of the accelerator is nearly similar to the cross-section of fluid flow, but all velocities point in the velocity vector diagram of the XY plot is nearly similar to the cross-section of fluid flow. Uh, uh, I'm sorry. Do you want to make? I do not understand. Sorry, Siddharthan. Do you want to elaborate? So right now we're dealing with a two-dimensional flow, right? So it's like water. Let's say water flowing on a plane. Okay. Uh, Now you have the velocity vector, uh, which has, let's say, two components, which is supposed to have two components. You're considering flow on a plane. So the x and y components are functions of points in time. So it's a vector valued function at each point in space. So it's a vector at each point in space. And that gives you the flow profile. Okay, so I actually have nothing else to discuss today. That covers more or less week one's material. Do you guys have any comments or questions?
I have a question, ma'am.
Yeah.
Ma'am, could you like say in a sentence like what is actually this what is this called hypothesis? What continuum hypothesis?
Continuum hypothesis, okay, in a sentence. So I have the restriction of saying it in a sentence. Uh,
I
you
search
forget
internet.
about, you look at
Okay.
the fluid, sorry, go on.
It's actually a mathematical idea. Some Cantor set is coming in. I don't know, like why. How can you like take it from mathematical to this physical view with parcel in it? So how can you apply to this water parcels or
So
fluid parcels?
forget about mathematics because right up until now we have not associated any mathematical expressions to continue to the concept of continuum limit. As of now, we've claimed that our claim is that the continuum limit is or working with continuum just means that you forget about individual particles and you look at the entire system as a continuum. It's the same thing. It's I would not say it's the same thing, but so you could have uh, you could have taken this fluid parcel and tried to study the motion of every single particle. That could also, in principle, because you know how every single, let's say you're working with a bottle of water, right? You're probably, I don't know, shaking it, you're throwing away the bottle of water, you're throwing it at a wall, and you want to see the the flow of how the water would respond to such a force, let's say. Now, you could, in principle, work with the millions and millions and trillions of water molecules inside this uh, water bottle because you, in principle, know how every water molecule would behave to a certain level of to a certain force and how the water molecules interact with each other. You know all the fundamental forces, and now you sit down to compute the dynamics of all of these molecules. But then it becomes increasingly evident that it's impossible. So what do we instead do? This is where the continuum limit sets in, where we say that okay, what we will do is we'll look at this water as a continuum. That's all it means. We'll look at not as comprised of many different particles, many water molecules, but as a continuous fluid parcel.
And not a discrete one.
Absolutely, absolutely. That's
Hmm.
exactly similar to what happens when we're dealing with rigid bodies, right? So if I have my phone right here, it's made of millions of particles, but I don't treat it if I throw it at the wall, I wouldn't need to know the dynamics of every single particle in this whole. I will just need to know its center of how its center of mass behaves, and I can tell you with what acceleration it will reach the wall and what will it will break into how many pieces. These things I can conclude or say without knowing about the millions of particles inside this phone.
Okay, actually, may I just add one small line?
Absolutely, absolutely, yeah,
The thing is that like even dealing with three particles is an impossible task because chaos sets in.
yeah.
Am I
Forget
right?
about millions. Absolutely. The three-body particle remains unsolved. We have to apply simplifying assumptions, simplifying approximations, and the three-body problem can be solved in some simplifying limits. But so it's impossible to then we have to just give up on studying astrophysical systems. But that's not something we want to do. What we want to do is we'll say, okay, it's one continuous. This fluid, this system is one continuous particle, and instead of looking at every particle we'll look at a clump of particles. We'll call this a continuous some continuous object like a rigid body, like some continuous object but not a rigid body because it's a fluid particle. And we set up the premise by saying that okay, so this is a fluid parcel and this is a continuous object. We don't look at the part each individual particle inside this parcel, but we look at the behavior of this parcel and how it behaves in this entire fluid system, how it interacts with other fluid particles. The way it interacts is it'll have some viscous force, it'll have other interactions. We look at those, we look at the dynamics of the fluid parcels. Are you happy? Are you satisfied? Is this fine?
It's okay.
It's okay. Okay. I know that people are not happy with the fuzzy description of okay, how people would like a very precise definition of the continuum limit, and they would want to know, well, what is the exact value of NL cube that will tell me that okay, this is when the continuum limit is justified. I know it is quite fuzzy, but it's unfortunate. This is the premise we have to work with to get at least some zeroth degree understanding of astrophysical systems, of something much complex, of anything much complex. Otherwise, it gets even impossible to uh, studies the behavior of water. How are we supposed to store it? What behavior? What is the viscosity of water? We don't need to know the behavior of every single particle in a tank to know with what viscosity will each layer exert on the other, and so on. We sometimes have to work with some fuzzy descriptions to make for the better. I don't know, for the greater good. I thought the diagram might represent the cross section of a flow, seeing the increasing velocity at the center, but it was a wrong analogy. Okay, cool. No, so what we're dealing with, Siddhartha, what we're dealing with is just flow in, let's say, a 2D plane. And these are, so if you would like to see how fluid passes would move, you just connect the various different vectors and you can see it's a representation. You can see that these are the directions along which a fluid parcel would move. That's what the velocity vector tells you. Okay, any more questions?
Okay, just one small thing is that in one question it was mentioned that the flow of the fluid is much less than this velocity of the fluid is much less than the speed of sound. I mean, was that mentioned to ensure that the flow was steady and not turbulent? Was that the reason, or there was some other reason as well?
The reason was that the steady and turbulent flows have not been covered yet. All that meant was do not worry about the pressure being so large that the density of the fluid might change from point A to point B.
Okay, okay.
That's all it meant. That's all. That you're just dealing with regular incompressible flows. You're not dealing with insanely large pressure differences that it can actually compress fluids and so on.
No, suppose we are dealing with an ideal fluid, then
Ideal
in that
fluids are incompressible. Yeah, yeah.
so in that case it will be impossible to maintain a steady flow, right? So it will be a turbulent flow.
Let's see. Let's see when we cover steady flows and turbulent flows.
No, one small overview was given by Professor Prasad in the
Huh.
videos.
It'll be covered in greater detail in next week. But yeah, that's food for thought. Yeah, I'm glad you're thinking about next week's material. That's great. Okay, so if there are no more questions, I'll stop the recording now and I'll wait for 10 more minutes.
Ma'am,
Okay, yeah.
question.
Yeah, tell me.
Ma'am, I have a question from this Lagrangian frame and Eulerian frame.
Okay.
Ma'am, my question is right. Suppose you are in a laboratory, right? You are in a static frame of reference, like it's static, it's not moving, and in front of you is the flow of fluid in a pipe,
Mm-hmm.
and you're measuring some physical quantity that depends on your position coordinate and your time coordinate, and this position and time coordinate with respect to your frame position and time coordinate with
Mm-hmm.
respect to your frame because this the Cartesian coordinate you're saying that is in my frame only. It's the origin. Everything is situated in my frame. So from my
Everything is
point
being
of view,
computed with respect to me if I am in
me,
the lab frame. Hmm.
yeah, in my life lab frame. So suppose I'm measuring the total derivative of a physical quantity. So
Hmm.
I will write df. F is my physical quantity. So I will write df, and it's since the f is depends on x and t, I will write df equals to del f by del t into dt plus del f by del x into dx.
Mm-hmm.
Right. So
Mm-hmm.
everything this t, this the x component, the x coordinate, and the time t, these are all from my frame of reference, right? I'm asking this del f by del t into dt plus del f
Mm-hmm.
by del x into dx, this
Mm-hmm.
x and the time you are measuring.
Mm-hmm.
This is from my frame of reference, right? I'm asking this like where this it's from my point of reference, right?
What are you trying to compute now?
My I'm telling that there's a df, everything I computed, like the total derivative of the physical quantity. These
Mm-hmm.
are from my point of reference.
Yes, but
My point of,
understand that if you're in the lab frame, if
yeah.
you are static with respect to the flow, then it doesn't make sense to ask what is the total rate of change of a function f of this fluid. What you can find out is you will have two different sorts of uh, derivatives creep up. One would be because of the explicit motion of the fluid parcel in time. That will be given by the, let's say, del F del T. This T is, of course, with respect to U.
Hmm.
And another, and you'll also obtain difference, and the function F will change with respect to U also because of there could be some things happening locally at different points in X, and that can give you a change in F. So there are two sorts of changes creeping in F. One, because you can actually see the fluid parcel moving in time,
Hmm.
and because some things might be happening locally in X.
That X is also from my point of view, right? I'm asking
That
this.
is correct. That is correct. Yeah.
Then why he is telling that df, the left hand of the equation, that is
Mm-hmm.
df, that is
Mm-hmm.
a Lagrangian frame, that he said like someone is sitting on the
Mm-hmm.
this fluid parcel, and
Mm-hmm.
he is measuring the same thing, same physical quantity is measuring by sitting on a fluid parcel.
Because
So
see, the just because of frame changes, clearly there is a frame of there's change of frame. Clearly,
yeah.
you're making a Gaussian frame transformation
Hmm.
because you're dealing with low velocities of fluid parcel. Let's say we're in the non-relativistic regime, and you're working with Galilean frame transformations. So when you go from the Lagrangian observer to the Eulerian observer, there's a frame change.
Yeah.
But just because there's a change in reference frames does not mean the physics have to change. In fact, it would be disastrous if the physics were to change. These
Yeah, both
quantities
are
have to
right.
be
Okay.
these
Both are
quantities
right in
have to
their
be
own
frame
perspective.
invariant.
Okay.
Right,
Hmm.
right. Now, the way these, of course, they have to be equal because the physics stays the same. If there's some change happening, uh, there's some temporal and spatial change happening with respect to me, who's a lab observer. There must be some changes happening to you, who's, let's say, the Lagrangian observer. Now,
Huh.
these changes have to be the same, but there should be a way to relate these two changes, and that is given by the equation that I mentioned in the class.
Okay.
Is that fine?
So
So it's fine if you're right now confused. You can go back, think about it, and we can once again discuss this in the next live session. Uh, but sure, bring it up again if it still confuses you.
okay.
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 Okay. Are there any more questions? So I'll stop the recording now, and I'll wait for